Hello, my name is Greg Buehrer, and I'm the head of product and the CTO of Azure Machine Learning. Today, what I want to talk about is building generative AI applications, and specifically how we can make that scale. So Microsoft really does run on Azure. All the Copilot offerings that we've released recently, they all run on Azure in Azure Machine Learning. The workloads are amongst the most complex and largest in the world. Today, we'll explore how we think about how we can bring this to a cloud platform so customers can do the same. To accomplish this, the way I think of it is we need to scale along 4 dimensions. First, we need to have an expansive offering that allows customers to meet their business needs. And these scenarios will be pretty variable. We also need to host and infer a large model at scale. So we need to have high throughput, low latency. We need to have GPU utilization. The model probably doesn't fit on a single node. It's very complex, and we need to do that very efficiently. Third, once the application is built from the customer, we need to be able to scale that application as well. And lastly, and probably most importantly, we need to have a broad but deep offering with respect to network security, the authoring experience, CICD integration, and the way of work that we can accommodate for the customer. Because all these enterprise customers have varying degrees in their environment for network security and things like this, and we want to be able to meet them where they are. So first, let's take a quick primer course on large language models. LLMs are mostly generative models that output text when given a prompt or a question. They're trained with vast amounts of data. They have billions of parameters. They take weeks, sometimes months to train on thousands of GPUs. Just as an example, with 16-bit weights, a trillion parameter model is 500 gigabytes on disk. So even just moving it around the network is actually quite complex. And while there are waves of compression, like sometimes the models get a little bit smaller, you'll see things like Llama on my desktop and stuff. In general, the principle is these models tend to get larger over time. So I don't think this problem is going away anytime soon. The basic building block of these LLMs is the transformer. Essentially, it's a neural network block that includes a masked multi-head attention unit followed by a feed-forward network. This multi-head attention can stretch far into the past from the input, probably like over 1,000 words, sometimes 2,000 words. And what this means in practice is predicting the next word is a function of all the words before it, not just a few words. That's what it was like in the past. But by using these attention heads and training over trillions of tokens, the model learns complex patterns in written communication that ultimately generalize well to a wide variety of tasks. In the example above, the word company has attention weights to each of the words before it, but the word meta has a disproportionate attention weight. Also notice in the diagram on the right, the interactions of the query, key, and value matrices. These matrices are going to come up again later, so I just want to point them out. For scaling our ability to tackle many different scenarios, we want to answer basically 2 questions. What is the array of practical use cases that are going to come up, and how can we build proper development software to support them? Our understanding of LLMs is getting better all the time. I would say when we looked back a year ago, we weren't quite sure what it could do and what it couldn't do. I think we have a better understanding now of what it can do and what they don't do well. But we see 4 areas where LLMs work really, really well. And these each have their own scenarios, a wide variety of scenarios. But generally speaking, we are addressing content generation, content summarization, structured output generation, things like code output or slot filling of functions, and finally reasoning. Usually the reasoning is over a large amount of data, which is typically from customer input. It can be quite complex depending on the model. For example, math problems, puzzles, customer enterprise, consumer data, or really a large variety of things. And what you'll see is in this RAG pattern that we call it, the scenario is really like bring your own data to the reasoning engine. Most important to the design process of this app is the ability to tune the prompts. Because LMs can alter their responses with just subtle differences in the input, for example, a single word change or a space or a period or the length of the prompt, other little tiny details tend to make a big difference. The ability to alter the prompt, measure it quickly, and iterate fast, and measure the quality of it ends up being a really big factor. And so we build for that. Here we show several common prompt formulations. First, there's a simple prompt for generation. You don't do anything except ask it a question. Next, we have something we call zero-shot classification. So zero-shot is when you ask the model a machine learning task that it wasn't actually asked to train. We didn't explicitly train on it, but we can ask it anyway without any examples, and they tend to do quite well. After that, we have the same task, but what we call few-shot. We give it a couple examples, and then we ask it to complete the question. Here, it does even better. And lastly, we have the RAG example where I was talking about before, where information is extracted from a data source, injected into the prompt, augmented, and then sent as part of the query. So to solve all these problems, we've built Azure Prompt Flow. Prompt Flow is a prompt authoring and evaluation tool built natively into Azure Machine Learning. Users can author in a variety of IDEs. Above, I'm showing the UI, but you can also author in SDK or from the CLI and things like that. It's highly flexible, has a managed API connection for integrating with data sources across dev, test, prod. It has custom Python support. It has native support for many common services like Azure OpenAI or OpenAI and a bunch of others. Also, it can use any framework. So for example, you can use LangChain, you can use semantic kernel, and it can be used for a wide variety of solutions. It's very, very, very flexible. And I think the big thing is that it thinks of evaluation first. So whether you built it in LangChain or not, when you come to the platform, it's focused on evaluation. We know that once a developer understands roughly what they're trying to do, the big hurdle is making the solution good. And what we did, we put that hardest part first. So we said, we're going to help the developer bring data science to the problem. One, we have a bunch of metrics that help you minimize hallucinations, errors, inappropriate responses, and other outputs that lower the overall effectiveness of the solution. I'll go over those a little bit more in detail later. A key challenge from the service side is hosting very large models at scale. They have to be low latency, you have to be able to deploy them quickly, and they have to maximize GPU utilization. A typical ML platform generally has two pillars, training and serving. They're supported by data sources such as a feature store, asset registry, probably an embedding store. They have workflow engines, Kubeflow, Azure ML pipelines, which is my favorite, Prompt Flow, that's also a favorite. And they have APIs that cover latency versus cost options. So for example, you can have an endpoint. It can be a batch endpoint for inference. It can be an online endpoint for inference, which is sort of a real-time single request. In the new model of generative AI, the need to optimize the inference side is growing. So honestly, like training is still important, but it's sort of shifted to a lesser priority as people tend to leverage these pre-built models because they get all the scale from it. Within inference, the three key performance goals are the kernel, the model, and the scheduler. Here, I'm kind of mixing the scheduler and the router because they're so intertwined, but we need to optimize all three. And the kernel, we optimize with Onyx. The scheduler, we optimize with advanced routing and batching using a tree pattern where the decision point in the tree has real-time information, and the batcher can use this real-time information to decide where to route the request. Essentially, we get to map similar requests to similar engines. Note that in traditional machine learning, batch workloads usually download the model to a local instance and infer locally. Here we can't really do that because the model's so big. So for batch, even for batch, we have to use really a real-time endpoint. And what we do there is we built in priority. So you can run these in the evening or something like this where your workload is lower. If you bought capacity for an LLM or you're hosting it yourself even for an LLM, the GPU utilization will go down on a diurnal pattern really pretty much no matter what customer you are, because your customers that are in that local region don't want their data to leave that region, so that endpoint tends to be served in that region. And in that case, then you just get less traffic at night. So that's how we have priority, which automatically kicks in at night. We briefly touched on how transformer models work. Attention blocks are an expensive portion of the computation, but with the decoder-only model, the query key and value computation can be cached. And you can see that in the picture. The majority of the matrix is the same, and you just append one more embedding on the end of the matrix and then do your computation. So because of that, you can cache this. We call this the KV cache. we leave out the Q because Q is mapped into the K at runtime. But this significantly reduces the computation of the attention heads during the generation phase because all that computation is just reused as this autoregressive model predicts the next token in the output. And that's a way to think about the model. The model, when it gets back the input with its token or the word that it predicted from the time before, it's like it doesn't know anything. It's starting all over again, except we did cache the matrices. But other than that, it just thinks of it as all input. And we do this by tracking the available cache and passing that information up the routing tree to the decision layers so that at each layer in the decision tree, we can decide, is there available cache in certain instances of the model? We also factor in batch size, prompt length, locality sensitive information because that will improve caching because they tend to have a higher prefix overlap and generate better cache hit rates. There's a paper on this. I put it at the bottom of the slide. It's a really good paper out of Google. It's a fun read if you have time. So given we can build generative AI applications, we can host a large model at scale. The next thing we need to do is scale the customer's deployment. Consider, for example, like a large online retailer who's deploying an advanced customer agent. Traditionally, what I've found is that a regular machine learning model is really nice to have. The SLA on the model inference stack tends to be like 3 nines. The SLA on an application for a large retailer is 5 nines or 6 nines. So this application has to run all the time. To do this, we need to address 3 needs. We need to scale the customer LLM application endpoint. Essentially, once they build this prompt flow, that prompt flow goes on an endpoint. It offers A/B testing and these types of things. And we need to make sure that thing can scale. We need to offer low latency, high throughput of responsible AI to protect the endpoint. So we have a service. It's called Azure Content Safety Service. You can plug it in, and no matter what model you're using, it can be an open source model, or it can be one of our hosted models, but that model can be protected with Azure Content Safety. For Azure OpenAI calls, for example, that model is built in, so you don't have to use it. But it's a great service. And we need purpose-built monitoring for these endpoints after we deploy them, which is super important. And we'll explore that in a bit. Within the prompt flow offering, we have one-click deployment to our scalable managed inference stack. We already built a stack. We know it scales to billions and tens of billions of requests a day. We can reuse it. We've seen it on Copilot. We've seen it with Bing. It's been shown to scale really well. It has an auto-scaling feature that can be used to increase the serving replicas based on RPS or requests per second, that it dynamically adjusts your spend and how many containers you're running. It has a lot of other production quality features like A/B rollout and these types of things. It's also a managed VNet, which makes it easier, and you can customize that managed VNet however you want. We also support exporting the prompt container so you can run it on anything you want. So whether you run it on your own K8s, you want to run it on AKS, you can run it pretty much anywhere. We want to be flexible and meet the customer where they are. As mentioned, with any deployed application, monitoring the health of the application is a P0. In Azure ML, we built this purpose-built monitoring for LLM applications. By default, the system captures a bunch of things for you for free. It captures token count input, so the prompt lengths. You can measure the average prompt lengths. I guess it goes this way. Output token count, latency, and a bunch of other specific system-level metrics. These metrics are then pushed to Azure Monitor or pushed to wherever you want, and then you can track them in sort of a global single pane of glass for all your endpoints across all your workspaces, and which is super helpful. In addition, we compute quality metrics at the interval that you choose, such as relevance, groundedness, coherence, a bunch of other metrics that I mentioned earlier. In both cases, the sample rate and which metrics are computed is fully controlled by the customer, and you can define your own custom metrics, which personally I find super satisfying because I have my own opinions on what I want to measure. And it helps a lot just to be able to write a script, Python script, dump it into the model data collector, and it just works. And as I mentioned, Azure Content Safety protects our endpoints from malicious queries, rogue or harmful outputs. Probably most importantly is scaling customer reach. Customers have widely varied needs and ways of work. They have widely varied mechanisms on which they secure their network. They have different who builds these applications varies widely. You could imagine for a generative AI application, maybe it's the data scientists, maybe it's the developers. Actually, I see a fair split of both, although I would say that most groups are leaning towards developers just because of the production requirements. And how they choose to productize these with CICD is different. So the platform really needs to be able to snap to that. And this is probably the single biggest blocker that I see when we try to go to production is that we can't meet the solutions that are provided don't always meet the security requirements that the customer has based on their particular topology of their VNet. So first, let's talk about different experiences. For authoring prompt flow, we offer a bunch of them. We offer the GUI. I showed you that a little bit earlier. We offer a code-first experience with the Python SDK. We have a command line experience that's very rich, also automatable, and we have REST APIs. For a lot of endpoints that I use, I actually interact through REST APIs. It's quite easy, simple. I know it's going to work. I don't have to deal with any of the overhead of what my code environment is. And what I would say is when we design the REST APIs, we try to put the business logic on the server. So in all these experiences, you get the same business logic. But most importantly, regardless of which ones you choose, each experience has the full capability of authoring prompt flows and deploying prompt flows and actually is editing the same assets. This last point, editing the same assets, is important because besides just moving between experiences, like say maybe I started in a GUI and then I went to a code first experience, it guarantees that like the downstream services that host this, that run CICD and everything are consistent. You use the exact same one for all of that because you're editing the same assets. For us, a prompt is a first-class citizen. We mentioned earlier we have built-in evaluation with prompt flow. Again, this is critical to drive quality in the solution. The metrics, coherence, similarity, fluency, relevance, pairwise relevance, groundedness, accuracy, F1 measure. We're adding to it regularly. The one I really want to add is jailbreak, but I'm trying to work through some regulatory stuff. But that one I think is also super important, particularly if you have a chat agent. But as I said, like the greatest blocker is deploying this in a secure environment. And enterprises have a lot of different network security implementations. In particular, GenAI workflows, they often call other data sources during inference time. So if you think about what the business logic of a GenAI application part, that GenAI part is, it's not just a call to the LM. It could be a call to a database. Then it's post-processing the data set. Then it's reducing or chunking. It might make multiple calls to the LM. It's working through a bunch of things that it might be calling an API that you've hosted an OSS model. So when it's working through all these different API calls, those aren't natural to inference environment. An inference environment tends to be a static read-only model. You send in data, the HTTP comes back with the response. So here we need to build for that. And that requires typically explicit routing policy on the VNet. So if you're running a sort of a no public IP VNet and you need to access a service, that service needs to be mapped with a private link. And here we make that easy for you. We've included extensive support for it, including role-based access control. So it's not like the data scientists can suddenly, open up a bunch of holes in the VNet. That's controlled by the admin and through policy, through role-based access control. And this is really like the core of what makes a service productizable, like productionable, is being able to meet the customer where they are in their security environment. And then lastly, I just want to point out that all enterprise customers have a tightly controlled process that takes their CID, using CICD, that takes their solutions from dev to test to prod. And that's the right way to do it. And to adhere to that process, we have to actually be working on files and folders. That's how code works. That's basically, you need a durable asset that's well-defined that will adhere to the CICD process. So as mentioned, our prompt flows are YAML files. They reference components in code that are also files. This is true regardless of your authoring experience. And that really helps you, the company, maintain their existing security policy and their existing productization policy. Then you can use standard AZ commands, Git commands, our own CLI to automate the process for CI/CD. I hope you enjoyed our discussion on generative application development in the cloud, specifically on Azure with AML and PromptFlow. As always, feel free to reach out to me. My alias is my last name at Microsoft.com. Thank you for joining. Have a good day.